All right, let's dive right into this explainer. Today, we're looking at a fascinating new system called Director. We're talking about a massive breakthrough that completely rethinks how we serve giant AI models. You know, if you've been following the AI space, keeping latency low as models scale up into the stratosphere is easily one of the hardest infrastructure challenges out there today. Well, Director actually tackles this head-on with online, proactive expert placement, and I've got to say, the results are honestly game-changing.
We've got a clear roadmap for this today. First, we'll cover the MoE's serving bottleneck. Second, Director's proactive approach. Third, solving the placement puzzle. Fourth, prototype benchmark results. And finally, what developers should track. Let's jump right in.
Section 1. The MoE's serving bottleneck, and exactly why these trillion-parameter models tend to stagnate.
So, just to make sure we're all starting on the same page, we need to quickly touch on expert parallelism. This is the standard, yet highly demanding architecture for running models with trillions of parameters. Think about it, since you can't just cram a trillion parameters onto a single chip, and you definitely don't want to compute every single parameter for every single word, we use what's called a mixture of experts. This selective activation is great because it keeps the required flops sublinear, but the catch? It forces us to spread those experts across multiple GPUs just to manage the sheer memory footprint. And this is exactly where the bottleneck rears its ugly head. A forward pass through each MoE layer demands these two specific all-to-all communication steps across your entire GPU cluster. First, you've got to dispatch the tokens out to whichever specific expert was selected for them. Then, after the computation is finally done, you have to aggregate all those scattered results back together.
Because the hidden state of every single token must literally physically move across the network during these operations, we end up with a severe communication traffic jam. The network I/O simply cannot keep up with the raw compute speed of the GPUs. Your end-to-end latency basically becomes completely dependent on how you've placed these experts across your cluster. If related experts are far apart, your data's traveling further and your serving speed just absolutely plummets.
The contrast between our current historical approach and what the future requires is wild. Right now, systems look in the rearview mirror, at past requests, to guess where experts should live. It's a totally reactive approach. But live inference traffic constantly diverges from the model's original training data, right? When workloads shift rapidly, static placement leaves you with a persistent load imbalance. Directress just throws that whole idea out the window in favor of a proactive placement system that adapts dynamically.
Which brings us to Section 2, Director's proactive approach. How exactly do you forecast inference demand and place an expert before the request even arrives? Well, instead of reacting, Director predicts incoming traffic using one of two pretty ingenious forecasting methods to spot demand shifts before they ever hit the GPUs. If you're on a tight memory budget, you'd probably use the lightweight cascaded predictor. Or if you need higher accuracy, you can opt for a low-bit quantized replica of the model. Either way, Director is essentially looking slightly into the future, figuring out exactly which experts are about to get hammered with requests. Now, here's the really clever part. When Director decides to actually move an expert to a better GPU, it hides that massive data transfer behind periods when the GPUs are already totally saturated with computation. The authors of the Infocom 26 paper highlighted this as the key to their online migration module. They aren't pausing your inference to move data, they are sneaking the data across the network while the GPU is busy crunching numbers.
It's kind of like moving the furniture around while the GPUs are busy looking out the window. Director achieves near zero downtime without disrupting active serving. The migration scheduler strictly decouples the prediction of what to move from the actual execution of moving it. That means your teams can run the predictor continuously in the background without ever blocking a live inference request from a user.
Let's move to Section 3, solving the placement puzzle, or the math behind the migration. Because placing these experts perfectly, it's an incredibly complex mathematical challenge.
This system has to rapidly solve what's known as an NP-hard problem without turning the placement calculation itself into a secondary network bottleneck. In computer science, an NP-hard problem basically means that as you add more variables, like, say, more GPUs and more experts, the number of possible combinations just explodes exponentially. You could easily spend way more time trying to find the perfect placement than you would save by actually moving the experts in the first place. So, to get around this, Director uses a super smart relaxation-based optimizer that guarantees a 1 plus epsilon approximation ratio. Instead of grinding your whole cluster to a halt trying to find the absolute perfect, mathematically flawless discrete placement, it relaxes the problem into a continuous domain.
This lets it find a near-optimal solution incredibly fast.
This mathematical bound acts as a crucial safety net. It ensures the system finds near-optimal placements and limits latency degradation, all while running efficiently in polynomial time. It guarantees that the system respects your hardware capacity limits and routes experts to the least congested nodes. But most importantly, that 1+epsilon ratio provides a verifiable upper bound. That means Director mathematically promises, that it won't accidentally make your latency worse while trying to fix it.
Okay, Section 4, Prototype Benchmark Results. A slick theoretical paper is great and all, but what actually happens when you put Director to the test on production architectures?
While the prototype benchmark results are pretty staggering, we are looking at a massive 11 to 55% reduction in end-to-end latency across absolute heavyweights like Mistral, DeepSeek, and Qwen. Compared to existing baseline placement strategies, cutting your latency by over half in the best-case scenarios is just a massive win for both user experience and pure compute efficiency.
And this data proves a really vital concept. The cost of prediction-driven migration actually pays for itself the exact moment live inference traffic diverges from the original training data. The benchmarks validate that the latency gains scale directly with the volatility of your request patterns. When users start throwing unexpected prompts at the model, a static system just crawls, but Directors dynamically rebalances and keeps your throughput soaring. Finally, Section 5, What developers should track. Director might be a research prototype right now, but proactive infrastructure is very clearly the future.
When Director or similar frameworks eventually hit open source, engineering teams are going to need to immediately focus on 3 critical integration steps to prevent network overhead. First, you've got to calibrate the predictor to your specific workloads, because mismatched forecasts will just trigger useless migrations. Second, you must verify the safety of your compute-bound detection logic, making sure you add fallback timeouts just in case unexpected network congestion causes a migration to overlap with active inference.
And for step 3, tightly managing your memory constraints is everything. A mid-migration out-of-memory error? Yeah, that would completely defeat the entire purpose of the optimizer. Remember, you are temporarily duplicating an expert while it moves from GPU A to GPU B. You must have the capacity headroom for that. So pin those memory limits and heavily monitor your control plane bandwidth during peak loads to ensure the optimizer itself isn't eating up all your resources. That wraps up our explainer on Director's proactive expert placement. It definitely leaves us all wondering how quickly this predictive paradigm will become the new standard in MLOps. The days of static, history-based routing are definitely numbered. By looking ahead, we can finally unleash the true speed of these massive MoE models. Keep an eye out for this open-source release, and honestly, start thinking about your capacity headroom today. Are you chained to the past, or are you ready to predict the future?